Albert Einstein once said, "The world is a dangerous place to live in, not because of the people who are evil, but because of the people who don't do anything about it." And we will try to do something about it by first studying cryptography. Cryptography. The word comes from two Greek words, cryptos, which means hidden or secret, and graphy, which is the process of writing or recording. Cryptography is the study of secure communication techniques that allow only the sender and intended recipient of a message to view its content. Cryptography in itself is a sub-branch of cryptology alongside with cryptanalysis. Today, we will have an overview of cryptanalysis and a general introduction of cryptography. Cryptography itself has two main types, which are symmetric and asymmetric. We will be focusing more on the asymmetric type because it is heavily used by distributed ledger technologies and the blockchain. Asymmetric cryptography itself has three main fields, which are DLP, which simply means discrete logarithm problem, and ECC, elliptic curve cryptography, and the most used crypto system, which is RSA. Now let's talk about Alice and Bob. Alice right here and Bob value their conversation as something that should be private between them. However, they are skeptical that this evil entity right here exposed their conversation. So Alice and Bob realizes that they need a technique to protect their conversation from the evil. This technique evolved into something called cryptography. They sometimes talk directly head-to-head or via a communication channel. This communication channel could be anything. It could be a telephone or the internet or some kind of network, and they exchange messages between them via this channel. Alice encrypts messages and send them to Bob. Then Bob decrypts the messages. This evil right here, he listens to all messages sent between Alice and Bob and attempts to decipher them, to decrypt them. Okay, so what if Alice right here have a message called M? He wants to send M to Bob via, as we said before, a communication channel such as the internet or anything. Let's call it channel right here. So if he decides to send M directly through this communication channel, both E, which is the evil, and Bob would have access to M. They both would receive M, but as we said before, they value their they value their conversation as something that should be private. What if this M is something that is super private? For example, a message of hello. Now we don't want this leaked to E. Now let me erase all of this. So Alice right here, he has a genius mechanism. So what he does is that he creates two boxes. The first box, let's call it F. And the second box, let's call it D, the D box. So the F box takes in messages. This message could be anything, by the way. It could be an image, it could be a file, a database, it could be anything. It takes a message M and it messes around with this message. For example, it can intercept this message and turns it into something that is unreadable. For example, we take the H and we substitute it with an exclamation mark, and then we make a type of transposition, which is just changing the position of letters between L and E. For example, I put the EL and then I put E, and then I append something like X at the end of the file. I would have something that is clearly unreadable, some like an exclamation mark lex. Now this doesn't mean anything, and let's call it C. Okay, so this C, Alice sent C instead of sending M through the communication channel. Now both the evil and Bob would have C. What does Bob do? He puts C in his D box. Now what does D box do? Somehow it could recognize that the exclamation mark means an H. Whenever he finds L and E, he somehow knows that this is this E should be before L. In general, it takes the C, which is unreadable, and it turns it to its original readable form, which is M. Now, as long as the evil doesn't have access to D, he would never be able to know what does C means. This whole process of turning M into C via F is called encryption. And taking C, which is something that is unreadable, and turning it into M, which is totally readable, via D is called decryption. And this, in general, is cryptography. Now we can summarize all of that, all of the description of encryption and decryption via symbols. Let's use mathematics. Now don't be scared. Mathematics is just turning all of that description into few symbols. So we have the box F. So instead of drawing F like a box and give it a message with M and do the arrow, let's just do something like this. And we give it the message M. Now F of M, it gives you C. And Bob right here has a similar thing, which is D, the D box. You know, the D box is a function. This function takes C and it gives you M. Now C right here goes through here and it goes through here. Now this is the equation for encryption and this is the equation for decryption. Now let's talk about modular arithmetic. Now modular arithmetic is heavily used in cryptography, so it is very important to understand. It is a system of arithmetic for integers where numbers wrap around when reaching a certain value. The good thing is you already know modular arithmetic because the clock that we use every day uses modular arithmetic. Okay, so the cool thing about modular arithmetic is that you wrap around a certain value, as we said. Now, in our clock, this certain value is 12, okay? So the maximum value that we have in our clock is 12. If we, for example, have the number 15, we want to know what is 15 hours in our clock. We simply start from 0 and then we add 1, 2, 3, 4, 5, 6, 7 until we reach 12. Then we wrap around this number and we say 13, 14, 15. Now, what is 15 in our clock? That's 3. So this is the cool thing about modular arithmetic. Now, let me explain by another example. So if I want to represent 28, for example, I want to know what is 28 hours in my system. Now, clearly, I don't have the number 28 in my clock. So what do? Again, I add, and then we notice that I wrap around one time, 0, 1, 2, 3, 4, 5, 6. I wrap around the first time. Then it will be 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now, this is the second time that I wrap around this number. The first time I did the full circle. So that's one time I wrapped around this number. Then I wrapped the second time, 13, 14, then reached 24. But still, I didn't reach my number. I want to know what is 28. So I keep adding 24, 25, 26, 27, 28. So 28 is represented by 4. How many times do we wrap around the number 12 given the value 28? And we can represent this in a simple Euclidean division. 28 divided by 12. So we are saying how many 12s there are in 28. So we are wrapping around 12 a certain amount of times. 28 divided by 12 would be 2. So we wrapped around 2 times. 1 and then the second. 2 times, then 2 times 12 is 24. Then we do 24 minus 28 minus 24, that would be 4. So the answer is the rest of the Euclidean division. Now this could be summarized by saying 28 mod 12. And that is 4. By mod, we simply mean the rest of the division of 28 from 12. And the rest would be 4. So we can represent any value in our small and finite set. Why do we use modular arithmetic? We use modular arithmetic mainly because our computers have limited amounts of memory that can represent information. So the smallest unit in computers, as you all know, is called a bit. And a bit could either hold a 0 or a 1. And we have finite amounts number of these bits. We don't have infinite amounts of that would be an infinite computer, and that doesn't exist. So we have finite amount of memory, and it looks like this. So when we reach a certain amount of value, we wrap around this number and go back here. Similarly to the clock that we discussed before. So if we start from here, go and start incrementing until we reach the final value. Now what do we do if we have a bigger number that then our memory could represent? We simply say mod the maximum value. So if we have an x, we want to represent x, which is a huge number, for example 25.87 billion, and we want to represent it in our memory. So we do a mod operation of the maximum value that our memory can hold, which is 2 to the power of k, where k is the available bits that we have, and 2 because each bit could have 2 possible values, either 0 or 1. Now let's talk about the Caesar cipher. The Caesar cipher is really famous, and it is really simple. If we have a plain text, which is obviously composed of the alphabets, we want to represent each letter by another letter. But how do we do that? We shift the alphabet from A to the right or to the left. So if I right shift by 1 position to the right, I would start the alphabet from B. Then I say C, D, E, F, G, H, so on until I reach Z. Because I started from B, I have 1 position left, and I go back to the beginning, and I would say A. Okay, so the only letter that is left is A, of course. So when I reach Z, I go back to the beginning, then I complete. So for example, if I want to encrypt the letter B, B would be C. A would be B, B would be C, C would be D. So for example, if I have the text A, B, C, and I want to encrypt it, I look up through this table and I see A, it is represented by B. So I say B, and then I want to encrypt the letter B. So B is represented by C, and then C. C is represented by D. So A, B, C would be B, C, D. So if we have, for example, Alice and Bob and the evil entity, and let's say that, okay, so this is Alice, and this is Bob, and this is clearly the evil. So let's say that Alice wants to encrypt hello again and send it. So they first, Alice and Bob need to agree on a key. So the key right here in the Caesar cipher would be the position by which you are going to shift the alphabet, which is in this case 3, and the direction that you want to shift in starting from A. Right here we are left shifting, so we are going back by 3. 1, 2, 3. We start from X, then we write the whole alphabet. So it is a left shift by 3. Both Alice and Bob need to have this information, and they need to draw this table based on this secret key. So this is the secret that Alice and Bob agree to. Then they go away. So they start communicating via this communication channel. And then Alice encrypts this hello. So it would be encrypted by the H, as we said, would be E, and the E would be B, and the L would be an I, so that's another I, and the O would be an L. And he sends this. So this is the plain text, call it PT for plain text, and this is the ciphertext, call it CT for ciphertext. And he sends this, and it goes around through the internet somehow like this, and it reaches Bob, and also E, the evil, could have access to CT. So they both have CT. What does Bob do? He knows that this is a left shift by 3. So he has E, B, I, L. Now this time he looks in this cipher line. He goes E is represented by H, and B is E, and then O. Okay, so he got the plain text. Hello. Now let's talk about cryptanalysis. Cryptanalysis comes from 2 Greek words as well. Cryptos, which means hidden or secret, and this word analyien, also analyze. It is the process of analyzing information systems to understand hidden aspects of the system. It is used to breach cryptographic security systems and gain access to the contents of encrypted messages, even if the cryptographic key is unknown. So its most famous technique is called frequency analysis, created by a polymath Muslim scholar called Al-Kindi. Al-Kindi describes the process of frequency analysis as the following. Now, we get a ciphertext, first of all, that we want to decrypt. We call it CT for ciphertext. Now, this is completely unreadable. Its words are meaningless. You cannot read this because they are crypted. We get something readable, something long enough, for example, 2 sheets from anywhere, from a magazine or a book or anywhere. And the first thing we would do is that we count the percentage of occurrence of each letter in the plain text and order them from the most occurring to the less occurring. For example, we notice that A is the most occurring letter in this plain text by 6%. So A has 6% occurrence in the plain text. Then we found out that B is the second most occurring, for example, with 4%. Then we found out that Z is the third most occurring, for example, 1%. Then we do this until we finally count the occurrence of all the alphabets, and we find out that the less occurring, for example, is T with 0.08%. We do the same process in the ciphertext. We count the percentage of occurrence of letters in the ciphertext and order them. So we find out that T, for example, is the most occurring letter by 6%. Then Z, for example, is the second most occurring with 3%, with 4%. Then K with 1%, and so on and so forth until we reach the less occurring letter, which would be, for example, A, 0.08%. Now what we do is that we map the first most occurring letter in the plain text with the most occurring letter in the ciphertext. So A would be T, and we would fill this table accordingly for B, C, and so on. So B would be Z, and Z would be K, and Z, almost, so Z would be K, and so on. We try to decipher CT, the ciphertext, using this table. Now you might be asking, why does this work? That's because Al-Kindi noticed that some letters occur more than other letters in the dictionary, and that's why this works.